Okay, so we had to break there and wasn't a good stopping place, but if memory serves, trying to decide how did I know to do these conversions? Well, again, experience helps, but it really does. Whenever you get a weird unit set, the best question I can tell you to ask yourself is, what units do you want? What units would make sense there? If it's power and it's in the English units, you could go to watts, that's okay. But if you can get it to horsepower, that would make sense. One of the easiest conversions for horsepower is this one right here. The legend goes James Watt was trying to figure out the best way to feed coal to a steam engine, and he figured out 1 horse could lift about 550 pounds of coal at a rate of 1 foot per second. At least that's the legend I've heard of in more than one text. So I don't remember very many conversion factors unless I use them on a regular basis or unless there's a cute little story that goes along with it. So that's one that I do remember. One pony, 1 horsepower, is 550 foot-pounds per second. The only way I can use that is I have to understand that is pound force, feet per second. To use that, I need pound force here. To get pound force here, I've got to use this conversion factor. Anytime I've got pound mass, I can use this to get pound force. Okay. I've got one more example here. I've got an efficiency example we can look at. I apologize. I just realized when looking at the screen that the glare on my phone sometimes is probably not helpful. I will try to be more mindful of that. Right? I've moved my desk around since the last semester, and so the light source that I'm using is at a different angle now. So L3 and 4, this would be page 7. Well, this will be our last page or not, we'll see. Okay. So I'll write this one out. This will probably be 2 videos. The second one might be a little short, and that's okay. I've got an electric car consumes 380 BTUs to accelerate a 1,760 pound mass car from rest to kind of a weird unit here, 328,000 feet per hour. I thought about leaving that in miles per hour, and I thought, nah, there's already enough conversions going on here. Feet per hour will be okay. And this is on a level road. And so what we want to do is we want to determine the efficiency. Okay? So, again, you don't have to write the problem statement from your textbook verbatim. If you want to, you can. I've had people, and especially since if you want to do this completely digital, if you just want to do a screen grab or a picture of the problem from the textbook and then insert that on your page, that's okay. If you're if you're like me, you're probably just going to work this out on paper and scan that, take pictures of it, and scan that to a PDF or something like that. You do not have to copy down the problem statement verbatim. If it helps you, please do. I don't require that. Okay? If you've got an instructor that does require that, do that. That's okay. I don't require that. I look at my memory here. Make sure, yeah. Right. I'm getting low on memory, so make sure I've got enough. The biggest thing is what you want to do is you want to make sure you write down what are you looking for. If you write nothing else, write down what are you looking for. And then, instead of writing a problem statement, if you want, you can just translate that into your given information. Right? So, again, the process here is what are you looking for, what do you know, and then what are the fundamental principles you're going to use to try to get to a solution. So what do we know? Well, we know that I've got a mass of 1,760 pound mass. Another English unit problem, that's okay. The car is consuming, so I'm just going to say work consumed. I don't know what else to call that right now. Maybe I change that later, right? If you're not sure what to call it, you can take a stab at it and change it later. That's okay. We know it's starting at rest, so V1 is 0. We know the final speed is 328,000 feet per hour, which I might suggest let's just go ahead and convert that. That's a good place to put that. That's not a bad place to put that. 328,000 divided by 3,600, so this is feet per hour. Every hour is 3,600 seconds. So if I divide by 3,600, that gives me about 91.11 foot every second. That's feet per second. Okay, why would I do that? Well, I'm just out of habit, I convert hours to seconds. And I don't mind doing it in my givens. So here I've got both in case I need either one. Okay, I don't know for sure which one I'm going to need, but it wasn't too hard to do that right off. It's on a level road. That means Z1 is equal to Z2. There's no change in potential energy for the car. Okay, again, this is an energy problem, so let's think, what are the types of energy that might be important? Well, the kinetic energy, that's going to be based on the speeds. Potential energy, that's going to be based on the elevation. So if there's given information about those, let's write those down. We know it's consumed a certain amount of energy to do this. We want to know what is the efficiency of this thing. Okay, so again, what are you looking for? What do you know? What are the fundamental principles you're going to use to find a solution? Well, by definition of efficiency, your text likes to say that this is output over input. Again, I might suggest to you it's want. What quantity do you want? That's not good at all. What quantity do you want divided by what quantity do you need? That's one way you can think about it. Which quantity do you expect to be the smaller quantity? Which quantity do you divided by which quantity do you expect to be the larger quantity? Let me ask you a question. Do you assume that a car is going to consume more energy than is actually required? All right, if I've got a gasoline-powered car or an electric car, do you expect, if it's a gasoline-powered car, do you expect it's going to burn more fuel than it actually would have to? Or if it's an electric car, do you expect it's going to use more power off the battery than is actually needed for the process? Yes, it's going to. This consumed, this is my denominator. Right? I'm going to expect, if this car is consuming this amount of energy, I'm expecting this car is going to consume more than is needed. Okay, so the work in required, divided by the work in consumed or actual. Again, I know it's going to consume more energy than it needs, so that's my denominator. So I need to know if this car was perfect. We went to the physics store and bought the perfect car because it's the only place it's going to exist. What is the amount of energy this car is going to consume to cause this change in energy? Okay. So anytime I'm looking for an energy term, so this is how I find the efficiency. So I've got one equation here, and I've got two unknowns. I don't know the efficiency. I'm looking for the efficiency. I don't know the work in. So now we say, okay, well, what do we do? Well, we give up and we say, we don't know how to. This is too hard. I don't know how to do this. Well, that's what most people do. We're engineers. We don't do that. We actually look at it and say, okay, well, what else do I know? What's the next piece in this puzzle? What else can I use? What can I use to find the work input? What can I use to figure out how much work is required to do this? First law. First law, anytime I'm looking for an unknown energy quantity, the first law does a pretty good job of that. So if we draw this car, right, again, you could write out the big long equation, Q plus W minus Q minus W is equal to M delta U and all that stuff. You can write it all out if you like. Or we can just draw a terrible drawing of our little car here and say, well, what goes into the car? we're going to need to put work into this car. And that's it. Right? Now, they didn't tell us anything about the heat. So I'm going to assume that Q is negligible. I'm going to assume that there's minimal heat. I'm putting work into it, so I'm going to assume that there's not really any work going out of it. I just need to know what is the minimum amount of work that I need to put into it. If it is losing heat, and the real car is going to lose heat. If it's losing heat, then that means more work's going to have to go into it. This is what is the absolute minimum work required to cause this car to accelerate. Right? This is what it's actually using. We want to know what is the absolute minimum. If it's the absolute minimum, that's the car that doesn't emit heat. It's not extracting work out anywhere else. It's not trying to overcome a drag force or anything like that. So the only thing coming into this car is the work in. The entire left-hand side of the equation is energy in minus energy out. The only energy going into this perfect ideal car is just the energy going into it, the work going into it to cause the acceleration. So again, if you'll think about the first law in terms of in minus out is equal to change, it's a lot easier to write that first law equation because the only thing going in is work. The perfect car is not going to have no energy going out of it. It's not losing any energy. All of this work's going into causing the change. Well, if we assume that the internal energy isn't changing, and if the internal energy did change, that's additional energy that's going to be required to overcome that. If we knew the temperature increase within the car, and after Chapter 4 we could probably figure out what the internal energy change is for the car. But we don't know that yet. So again, in Chapter 2, unless I know the U values of the delta U, or unless the problem's asking for delta U, probably my only option there is to assume it's negligible. So the only thing changing for the car, because it's on a level road, and we're assuming that there's minimal internal energy change for the perfect car, the only thing changing is the kinetic energy. And it's starting out at 0, so it's V2 squared minus V1 squared over 2. But we're assuming V1 is 0, or we're not assuming, that's given to us. It's from revs. So the work in is going to cause the final kinetic energy. How am I on? You serious? I didn't start a timer again? Okay.